LDA. I repeat, LDA. For some of you, that might mean legal drinking age. However, not in this class. Hopefully, you're all legal enough to drink. But LDA in here means a reagent name. And this LDA, the L, stands for lithium. The D stands for diisopropyl, and the A stands for amide. So lithium diisopropyl amide. Okay, well, it's not really an amide as far as a C double bond O goes. That's the ending that we give some of these, right? So we've seen this kind of thing happen before where it doesn't really quite make sense, like acetylene, but it's really a C triple bond instead of a C double bond. Same kind of thing here in a way, but we do see a nitrogen, and this nitrogen is attached to two isopropyl groups, right? So there is a nitrogen attached to two isopropyl groups. Well, that's a negative because this nitrogen has only two bonds. And then lithium is going to kind of sit on top of it, make in a way some type of salt, and that's what we call LDA. LDA is commonly formed by treating what we call cooled tetrahydrofuran with diisopropylamine and N-butyl lithium compound. Don't really care how you make LDA, but that's traditionally where it comes from. It has a pKa of 36. That means that this is a very strong base. Not only that, but it's very cheap. So if I really want a powerhouse to come in and do a reaction as far as a base is concerned, LDA does a wonderful job. So in this next reaction that we have with alpha carbon and alpha hydrogens, it is going to use the combination of LDA and THF. That is the solvent that we put it in order for it to go forward. This base is going to come in and do a very powerful job, and that is it's going to make a site of attachment for us, and that site of attachment will be available to something if we want to bring in a alkyl halide such as CH3I maybe, or Br, or Cl, but bromo and iodo typically is the poison of choice again. What will happen is that I could take a ketone or I could take a carbonyl group, period. Most of the carbonyls will work. And this carbonyl compound, so let's just do CH3, CH2, carbon, double bond, O, and CH3. If I can take a carbonyl compound and react it with LDA-THF, and I throw into the mixture a halogenated primary alkyl group, a substitution reaction is going to happen here. Miss America comes in, Miss America does her job. This is actually Miss Universe now, not Miss America. Miss Universe comes into the picture, does a very powerful job of pulling a hydrogen off. And that hydrogen is an alpha hydrogen on an alpha carbon. And when that happens, negatives stay behind. And if I react it with this molecule, this halogenated alkyl group, well, this is slightly positive here, right? The carbon and the iodine are into a fight. Iodine is more electronegative. It's more of an electron puller. It can hold those electrons a little bit better. So this is a positive piece that can be added on to a alpha carbon. So my product here would be CH3. One of these alpha hydrogens will be replaced, and it will be replaced by this alkyl group, whatever is there on that iodo. So this is a very good way to chain elongate, and we've always said that that is very important. If I can figure out ways of chain elongation, then this is good news for me because this allows me to expand my organic more and more and more and more. Okay, so let's just do another example. I can use ketones that are in a ring, that's perfectly okay as well. So I can use that one, and we can incorporate LDA and THF. And this time, let's do, I don't know, ethyl bromide, CH3CH2Br. So the same kind of story happens here. We'll take a look at my ketone. My ketone doesn't get touched. I'll look at one of the alpha hydrogens, pull it off, and then what will go on in its place? Well, it's this alkyl group that goes on in its place. So CH2 and CH3 will go there at that spot. I could have drawn it here to the right, or I could have drawn it here to the left. It doesn't really matter. It's the same molecule no matter what I do. Up here at the top, well, one of my products could be my methyl group going here, and another one of my products could be my methyl group going here. So you do have choices in these things. You know, don't really think that only one choice is correct, because you could have a multiple number of them. So let's look at another example. Let's say that we've got a ring, and then off of this ring we've got a carbon double bond O, and then an OCH3 group, and we add to this LDA, THF, and this time let's do ethyl iodide. Okay, well, here's my carbon of the carbonyl. This route doesn't have an alpha carbon on it, right? That's an oxygen, so that doesn't really start anything. This has an alpha carbon, though. It's right there. So again, start with your reagent, C double bond O, OCH3, and this alpha carbon, a hydrogen is going to be pulled off, and a CH2CH3 will go on in its place, because that's what the iodo is bringing into the picture. Okay, so what if these things are unsymmetrical? What happens, right? Because this was symmetrical. No matter which side I picked, I would have ended up with the right answer. This side, it wasn't symmetrical, but I only had one choice, right? I only had an alpha carbon, and that was here, so I was forced to put the alkyl group there. But here, this was unsymmetrical, and I told you that you had choices here, and we just did one choice, but there is another choice. I maybe could have pulled the hydrogen off on the other side and put my methyl group there. So what would happen if especially ketones, that's always the problem, children, it seems like, with symmetry. If we have a ketone and it is unsymmetrical, and we have alpha carbons on either side of the carbonyl bond, well, we get a mixture, but how do I know which one is the major product and which one is the minor product? Well, the answer is going to lie in the environment that you put it in. So we've seen this before. Way back in the day, we talked about reactions that are thermodynamically controlled, and we talked about reactions that are kinetically controlled. So one is based on kinetics, which is speed, right? And the other one is based on thermo, which is heat. So if I have a choice, I have to figure out, am I in a thermodynamically controlled situation or a kinetically controlled situation? If it's kinetics that I'm looking at, it will say negative 78 degrees on the arrow. Okay, so that's the first thing that we have to decide. If we have an unsymmetrical molecule with alpha carbons on either side of the carbonyl, and those can be replaced, both choices will happen, one being preferred over the other. Well, you've got to determine what environment you're working in first. If it says negative 78 degrees on the arrow somewhere, that is kinetic. And if it doesn't say that, you assume that it's thermodynamic. Okay, well, if we're talking about kinetics, We're talking about speed. If we're talking about speeds, then probability and statistics are going to be in our favor. So you look for the one that's less sterically hindered. So with kinetics, you're looking for the more exposure. Whichever carbon has alpha hydrogens that are more exposed, that is the major product. With thermodynamics, you're talking about heats here. And heat basically is going to give rise to stability. So it's actually the carbon that is less exposed, and that's the one that you're going to pull from. So let me come down here and give you an example. So let's say that we've got a ketone. So I'll just start this ring again, double bond O with the methyl group here. And we are adding LDA THF, and we, let's say, are adding ethyl CH3CH2 bromide. And I want to know what goes on. Well, I don't really see anything as far as negative 78 degrees here, right? So that means this is thermodynamically controlled. It is in a thermodynamic environment. So my product, if it's thermo here, will be a ring structure. My double bond O, the methyl group is here, and I'll look for the more substituted one because more substituted is more stable. So that means that this carbon is more substituted, so my ethyl group from the bromo, ethyl bromide, goes in that location. However, if I see an arrow that includes negative 78 degrees, well, this is kinetics. It's all about speed now. It's not about stability. So my speed basically is more exposed, and that's going to be this alpha carbon, and my CH2 and CH3 group will go on in that location. So that's the difference between thermodynamic and kinetically favorable conditions. We've seen it before, it's coming back again, and you only have to worry about this if it's an unsymmetrical carbonyl. And most of the time those are going to come from ketones. Those are the ones that you're going to have some problems with as far as determining which one is my major product and which one is not. So without 78 degrees, the more substituted carbon, that's where your alkyl group is going to go. If it's negative 78 degrees, that's kinetics. So the more exposed, well, that's the carbon that it's going to attack. So that's the story with alkylating at my alpha carbon. So the next video, we'll look at another type of reaction. There's not very many more of them, believe it or not. So we're kind of whittling down all of my possibilities as far as these reactions are concerned that we're going to be focused on at least. So stay tuned. We're not quite there yet, but we're getting closer and closer.